Hello, today we'll be presenting to you about our automated irrigation system that we are designing for our capstone project this year. My name is Olivia DeRosier and my team members are Austin Waldron and Colton Moore. First off, I'm going to take you through our client statement. We plan to design an irrigation system for a golf course green that's based on the already existing system, the Turo Turf Guard. The client's current complaints about this system are mechanical errors that lead to flooding, the inaccurate local weather data that leads to overwatering, and the insufficient processing of data. We hope to fix all of those issues, as well as design a low-cost solution, design a power-efficient system, and design a fully automated system for our client. Our objective for our project is to improve the current automated system that golf courses are using. We will do this by producing more accurate weather data. We plan to do this by running an open source weather network in parallel with local weather sensors that we'll be building ourselves. We will process the irrigation data more efficiently. Currently they are outsourcing the data and we'll be writing our own algorithms to process it. We will design our system to have no mechanical errors that will result in flooding, and we plan to do this by using pressure gauge sprinkler heads. And while doing all of this, we will also implement the pre-existing features that they had in the Turo Turf Guard. I will now take you through some of our system metrics. So for moisture sensors, we're going to use capacitive sensors. We will get a reading in farads, but then we'll have to use a formula to convert that to a percent moisture. For our salt index, we are going to use a resistive sensor that will be the same thing. We'll have to use a formula to convert it into a salt index value. For our water flow, we will be measuring it in liters using inline flow sensors. All of the temperatures for our system will be recorded in degrees Celsius, and the water flow will be controlled in the line by solenoid valves. Additionally, we will be using Zigbee for our wireless communication, a Digi-XB Zigbee gateway as our wireless gateway. We'll be using Digi Remote Manager as a cloud to communicate from our gateway to our web interface. And our web interface will be stored on our local server. We'll be not using a public server. We're going to be building our own user interface that will communicate directly with our main microcontroller. And we'll also be building our own local weather sensors using an array of other sensors, such as a humidity sensor, a precipitation sensor, etc.
We have four main constraints for our system, including testing during the winter months. We will have to build test beds indoor to make sure everything works and to prove that it works, because it's designed for a golf course and the soil will be frozen. COVID-19 throws a bit of a wrench into everything, including this. So while testing, we will all be working remotely, we will be independently testing our strategies, and when we do have to get together, we will have to be social distancing properly. Time is another constraint for us. We have a specific time this needs to be done for, so we can't be late. And we have a budget. Obviously, we can't spend unlimited money on this. We have set that for $500 after roughly estimating the cost of parts. Here we can see the budget breakdown for our project. The wireless gateway will be provided to us, which saves us a $120 expense. The DigiRM is going to be the web hosting for our project, and that'll cost a $40 subscription. The XB chips will cost $150, approximately about $30 per node. Miscellaneous parts, including the sensor modules and other discrete components, will run us about $75. The microcontrollers, we already have most on hand. They would run us about $30, so we're counting it. Weatherproofing our sensor boxes, we really don't know until we get to that, so we're allocating $50. And testbed materials, we should have everything that we need already, but we're allocating $50 for that as well, in case we need to buy something to help us test. Total, this runs us just shy of $400, and we were planning on limiting it at $500, so this is very good news. The concept for our design is to have a system that meets the following functions. So the system will detect the moisture, salinity, and temperature of the golf course. The system will transmit data from these sensors to the user and the central processor. The system will also get weather data from the internet, and then the central processor will process this data and it will also control the physical outputs based on the data collected. With a system that is functioning completely improperly, it'll water the golf greens without over or under watering. It will keep users informed of the conditions. It will communicate between the sensors and the controller, and it will gather accurate weather data to help make decisions. Here we can see a general overview of our system. It'll be broken down into three main sections: the sensor module subsystem, the web interface and gateway subsystem, and the microcontroller subsystem. We will break these down over the next few slides and describe what they contain. All of the subsystems of our project are of equal importance. The system can't function without any one of them, so these are presented in no particular order. We will start with the sensor module subsystem. You can see a block diagram on screen. It shows the three sensors we need on the left-hand side, the microcontroller in the bottom center, which will process the data and send it off to the Zigbee module, which will communicate it. This system will be battery powered. The sensor module subsystem is designed to collect data from the soil and transmit it so it can be used to decide where water is needed. The module is designed to collect the moisture levels of the soil, the salt index of the soil, and the temperature of the soil.
So I'll now give you a little bit of a breakdown on the web interface and gateway subsystem. Here you can see my block diagram for this subsystem. The squiggly lines are wireless communications and the software connections are the straight lines. So the Mesh XB network will be wirelessly connected to the Wi-Fi gateway. The data will then be transmitted into a cloud where my SQL databases are able to pull data from the cloud and store them. The SQL database will directly communicate with the web interface to display the data, and our open source weather network will send data to our web interface. As you saw in the past slide, this subsystem includes a wireless gateway, a physical website, an SQL database, and an open source weather network. The web interface is going to display some of the data that we will receive through our wireless network. The displays that will be shown are a percent moisture time graph, a salt index versus time graph, an ambient soil temperature, the local weather data that is pulled from the internet, and then the local weather data from our sensors. We also could add a couple more things such as the water flow from our sprinklers, etc.
Hello, my name's Austin, and this is the microcontroller subsystem. So this subsystem is responsible for receiving all data from the greens, the external inputs there in that little peach box on the left, the flow sensors up in the blue box there, the squares, and the weather sensor, which is in the bottom right in the yellow box. It will then decide how to operate the solenoids up in the top in the blue, and send some of that data back to the web interface, which I've shown with the external outputs here and again in the peach box. It also includes a user interface with a 0 to 9 digit pin pad and an LCD screen down here in the red box. The weather sensor will be connected wirelessly and possibly direct, because we'll probably have one close enough to be direct. The user interface will be directly connected. The external inputs and outputs will of course be wireless, and the top blue box there with the flow sensors and the solenoid valves will all be connected hardwired. So for this subsystem, our microcontroller is the STM32F103RB Nucleo. We use it in our classes 487 and other software programming classes. It requires 5-volt input, and it has 52 general purpose input-output lines, meaning that we can hook up 52 different components in basic signals, so giving them simple inputs and outputs, which is what we're doing here. There's a few of them we will use USART for, for the wireless transfer from the external outputs we will use USART, but that won't take up very much either, so that's not much of a worry for this micro. Our rain sensor will be the LM393. It's 3.3 to 5 volt input. It outputs a digital signal, so a 1 or a 0. If the sensor has water on it, it connects two lines and a comparator goes low, outputting a low signal, meaning that it's rained, and a high signal, meaning that it hasn't. For our flow sensor, we have the 114991172 flow sensor. It requires 12 volts, and it's a half-inch inline, female to male, and it returns a value in 1 to 25 liters per minute, which will be measured using the analog to digital converter. Then the solenoid valve is 12 volt input again, which will be easy. It's a half-inch line. It's inline, male to male, so I'll have to get an adapter for that, but that won't be very expensive or hard to get. 1602 LCD screen for the user interface. It's 5 volts and it has two lines on it that we can output text to. And then the 0 to 9 pin pad is pretty self-explanatory. But it also runs on 5 volts. So the screen and the pin pad being the same voltage, and the flow sensor and the solenoid valve being the same voltages will be beneficial to us in our building process. So this is our testing plan. We'll begin with our preliminary subsystem testing, testing independently, working on our own subsystems that we outlined above. We will be ensuring that everything works as it should on its own. We will be doing this remotely. Then we'll move on to our system testing. We will need to test all these components together as a team to see how they work cohesively. We'll be building test beds for our actual sprinklers. We will be ensuring that social distancing practices are being followed, and possibly conduct testing in Olivia's garage, depending on whether or not we need the space. So this is our Gantt chart for our automated irrigation system. On the right, you can see in the blue column there, in the top, it says project, so that's to signify our project day. On the left, you can see there's this list of big titles. That's all our important days and tasks to be completed before project day. On the right, each one of these cells is shaded a different color to signify the time in which they're being completed, and each row is a different task, of course. And on this slide, we have a more zoomed in or close-up view of that task list on the left of that Gantt chart in the previous slide. Some important dates here: the prototype due date, February 24th, then the final product due date of March 12th, demo week in the first week of April, and then of course project day after that week on April 10th. On the right, you can see it shows who's doing what. For the most part, lots of these things are all of us working on our own portions of the project, so they're all team members, but some of them are individual and they're labeled that way. All right, thank you for listening to our presentation. Again, I was Austin Waldron, and Olivia DeRosier presented, as well as Colton Moore. If you have any questions, you can reach us at our emails listed below. Thank you.